Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you so much for the introduction. A very good day to everyone, and welcome you to the AI for Good Machine 5G Challenge webinar session. My name is Thomas Basco from the ITU. The Machine Learning 5G Challenge aims to create a community to solve network-related problems using AI and machine learning. And today I'm very excited to host another webinar titled AI Fuel for the Next Generation AR/VR. This session discusses how AI components like deep learning can greatly improve AR strategies, offering users improved interactions with their physical environment. Some of the striking examples, which will include simulation training for high-risk professions, defense and military strategy, VR chatbots, and for more realistic interactions. Also, physical environment mapping, such as digital twin for planning and resource positioning, as well as in-depth sensitive mapping for medical surgeries. As always, we are counting on you to help create an engaging discussion. If you have questions, please type them in the Q&A. For anything else, you can type in the chat. Without further ado, I would like to introduce today's webinar speaker. Today, we are very excited. I'm very excited to introduce Professor Rajesh. He is a professor in the Department of Electrical Engineering at the Indian Institute of Technology, Delhi in India, where he's also in charge of the Samsung Digital Innovations Academy. Professor Rajesh has been a collaborator for us for quite a long time, and I'm very happy that we have had good collaboration, and thank you for making time to join us to give us this interesting webinar. So the floor is yours, and good evening, Professor.
Thank you, Thomas. It's always a pleasure to interact with you and the other initiatives that you've been doing as part of the challenge that we had earlier, and now a speaker for a second or third time. So we always have an engaging audience, and there's a lot to learn for everybody, including the speaker, which today happens to be me. Thomas, are you going to share the slide set, or how's it going to work?
Yes, you can share from your side. Thank you.
Oh, I should go ahead and share it then? Because
yes,
I sent it to you, so I was hoping that you'd do it. Would you do that, Thomas, if it's all right?
I can do that, no worry.
Yeah, thanks, Vishnu. All right, so while the slide set comes up, let's talk about AR, VR, and AI. Now, all of them are extremely deep in terms of the consequences, in terms of what they can or cannot enable. So there's been a talk of AR, VR. There was this talk of Meta for a very, very long time. People are looking at greater and higher immersiveness in their interactions with fellow human beings. But there's also this need to interact more human-like manner with machines. So all of these is giving rise to a mechanism where augmented reality and virtual reality is going to become more commonplace, and the lines between reality, VR, and AR are going to blur over the period of time. So in today's talk, we will focus on one aspect of AR, VR, which is how does AI play a role here? So artificial intelligence by itself is something that has become extremely, extremely commonplace in the last 10 years. You love it or hate it, it is here, and it is impacting us in a manner that is quite substantial. So let's get into the presentation right away. So if you can move to the next slide, please, Vishnu, where we talk of the agenda. So why are we talking about AI in context of AR, VR. There's lots and lots of things that we can talk of when we think of AR, VR. There's this need for processing the data. Then there's this need for communicating data. And as you will see shortly, AI has a role to play in both. Then what are the challenges with AR, VR, and how can AI become a tool to solve some of them? And these are by no means the only challenges. These challenges, if you notice, are related more to acceptance of the technology than to the technical challenges per se. And these engineering challenges are important nonetheless. And then how is it that we can go ahead and fix some of these problems with AI? What is this concept of explainable AI? We talk of LIDAR because we're looking more at a particular aspect of AR, VR again. So when we talk of augmented reality or virtual reality, there are multiple modalities that come to mind. Now, by no means video and audio are the only ones. There can be other modalities as well, but today we are going to focus more on the vision related aspects of AR, VR. There is talk of haptics. There is vision and NLP, which is in any case commonplace. All of these have a role to play in AR, VR, but to keep this talk to an hour or less, we will have to focus on something. So the focus of this particular presentation is the aspects related primarily to vision and how AI seems to play a role in some important engineering aspects. We will look at some applications towards the end of the presentation today. Next slide, please. Yeah. So what is it that we are trying to do here? So there is this sensory world, there is this digital world. And for us to experience it without any confusion or with it seeming native and real, it has to be done in real time. It cannot be delayed. It has to happen. You have to experience it while it happens. So the sensory world and the digital world, they have to be combined, and they have to be combined in real time. And AI has a role to play here because there's a lot of data that needs to be processed for this to become a reality. So as far as the sensory world is concerned, there are two aspects here. One aspect of the sensory world is the endpoints that collect data. And the other end of the sensory world is the human being himself who experiences things around him. So you could have actuators, well, the kind that we are aware of are, for example, headphones to listen to what is being said, or televisions, for example, or projectors to see what is being conveyed. So you could either be consuming it as a human, or you would need devices that can sense what's happening around it, like a camera can or a mic can. And then all of this data has to be converted into a digital format so that it can be processed, so that it can be augmented, or at times converted entirely into the virtual space. So all of these things need to be done for us to make something like this happen. So AR, VR is about realism. Augmented reality to a very, very large extent, VR to a lesser extent, will work only if it appears believable. And for it to appear believable, there's a lot of processing that needs to be done. You need to look at objects around you. You need to be able to make sense of them in real time. You have to be able to track and see what they are doing as they move about in the scenes around you. So again, this discussion is more towards what you see, but the same holds also for haptics perception, where you want to feel the world around you. And in that case, the sensory data that we talk about is the sense of touch, where you have kinematics, and you have tactile, where you have the sense of force, and you have the sense of fine details in the form of texture of the world around you. Now, what happens is AI, even though quite capable, suffers from two primary issues. One of them is the relatively high computational complexity. So how do we make sure that they are fast enough so that they can operate on real time. Otherwise, you lose the sense of reality, and the experience suffers to an extent that it can cause difficulty rather than enjoyment. So what is it that we should do to AI so that it becomes usable in an AR VR kind of application? The other problem with AI, of course, is explainability, because it's primarily based on what you train your model to be able to do. Sometimes you do not fully understand the capabilities of the model in terms of what it can do or what it has learned beyond what you try to make it understand. So for that reason, introducing explainable AI also becomes critical if you really want it to perform the task in a manner that is usable. So essentially, in summary, what we're trying to say here is that the large amount of processing that is needed for AR and VR to appear believable, AI seems to be the tool of choice given all the tools that we have at hand today. And AI itself has a couple of challenges, and they will have to be solved along the way if we want this alliance to be successful. Next slide, please. All right. So what are the challenges with AR, VR? And this is very specifically, next slide, please, again, are very, very specifically a couple of engineering challenges. There are multiple other challenges that exist with AR, VR, just to name a few, to bring things in perspective. When you want to create virtual reality or more complicated issue of augmented reality, what you need to do is understand your surroundings, and then you need to understand the intent, and then you need to add that intent so that it looks realistic in the already existing environment. So augmented reality is something that expects you to do a lot, and therefore in terms of technology to enable such a thing to happen, there are lots of things that will need to be done, and a lot of them are already in place, but those again are discussions of other presentations that you've had over the last few weeks, and you'll continue to attend over the next few weeks and months. Today we're going to talk of something known as this impact of cyber sickness. What happens is when you try to experience the world in a manner that it should be, but that is not your reality, then unless it is presented to you in a manner that the nature does to us, it can be quite disconcerting. So if it does not match our nervous system's inherent latency and resolution capability, it can be quite irritating. It can lead to headaches, nausea, and such other symptoms. So rather than being an enabler, it could be a deterrent if it is not done properly. And why does this kind of a problem happen? Because what is essentially happening is that when you want to work with AR or VR, what you're presenting to the human or the entity is more or different from what is actually around him or her. And therefore, if it is not presented in the way the nature presents this information to us, it can be quite disconcerting. So what are the technologies that can play a role here, right? For example, when you use stereo cameras or multi-view cameras, you try to get the information of depth. When you look at the world around you, there are two primary types of visual cues that you're looking for. One is the information that is present, which means the objects, background, and the relationship between different objects. And the second thing is what is known as the range or the distance of those objects from you and from each other. So technologies like LIDAR, what they can do for you is that they can do the mapping for you quicker. So while a regular optical camera can collect information regarding the objects and background and activity that is happening in the scene of interest, LIDAR can help you with the ranging, because unless the shape, size, and depth is not correct, the experience is less than optimal. Neuromorphic imaging is another technology which is quite recent, and here they want to do imaging the way a human views the information around him, and this will help again overcome the problem of being presented with data which is not usable in its native form. Another technology which is making this happen is what is known as edge computing. Latency primarily, and a large compute capability, as the second requirement, are the drivers for AR and VR experiences being realistic. So edge computing brings the ability to perform complex processing and computations very close to the endpoint. And what this does for you is it reduces the latency. And when you have a low latency processing capability available, the realism in the renderings and experience goes much higher. And AI, of course, will continue to play a role here, because deep learning ontology is a mechanism for representing information. And then if you incorporate all of this into AR, then there are strategies that can help you improve the experience to a much higher degree. A comment here before we move to the next slide. We've been looking at traditional communication for a long time. Over the last 3 or 4 years, there has been a thrust in something known as semantic communications. So way back in late 1940s, early 1950s, when Shannon came up with his, well-known and all prevalent channel capacity related work, he had mentioned 3 levels of communication, he and fellow workers, where the first level is the traditional communication that we are doing today, syntactic kind of communication, where you convert information into a form that humans understand, and then you send it over a channel. So that's syntactic communication. They talk of level 2, which is semantic communication, where instead of sharing syntactic information, you simply share the actual information that a person or the other endpoint is interested in, rather than flourishing it with gestures or modulated speech or complex videography. What all that you need to do is make sure that the information or semantics reach the other end. And at level 3 is that information able to perform the task of interest. So if people start looking at machine-to-machine communication for the future, you will primarily be looking at level 3, because all that you're interested in is, did the communication result in the right outcome resulting? So at level 1, which is where we're working at today, is very quickly giving way to what is known as semantic communication, where you do not worry about the syntactic content. You're more worried about the semantic content. You look more at what is the core information that needs to be shared. And this I am talking about at this stage because this will lead natively to compression. This will lead natively to quicker rendering, and it will lend itself to much easier augmented reality, because adding and removing content from a stream will become much, much easier, because it will be knowledge driven. Can we move to the next slide, please? All right, so now some details. And some of these slides I'll spend some time on, some of these I might skip, but these are details to make some things happen. So what are the system components of a typical AR/VR system? So you need 2 kinds of things. You need sensors and you need actuators. So mostly when we think of AR/VR, we think of a headset with which we sort of consume content in 3D. And we have an immersive experience. You also have audio inbuilt, so you are able to hear what you need to, and you're able to see what you should in 3D. And on this, you can overlay information, giving rise to augmented reality, or you could reside entirely in the virtual world in way of VR. So what are some of the components that you might need to accomplish a task like this? So there's this need for head tracking, because now as the head moves about, you should see different information or different content. So you need to always keep track of where the head is, so that you can present to the consumer or the human the right information. And one has to be very accurate vis-a-vis the direction in which the head is pointed. Then comes the problem of rendering. So if you are looking at a particular direction, what is it that you should be seeing? So that of course is a given, but what is problematic is that as you move your head, how soon are you able to update the scene so that it matches the position of your head? So sometimes there is a delay here, and this is known as motion to photon latency. And this can lead to confounding experiences, and this is something that you would want to avoid. The best way to avoid this is that you track the head well, and more importantly, you have extremely low latency, high computational capability processing capability available. Then there is optics and field of view. So as you move your head about, you should be able to see things not just correctly, but also at the right depth. And the field of view should not seem unrealistic. Next slide, please. Okay, what are the, how do you resolve some of these issues? Yeah, okay. Now, explainable AI is something that will help you overcome some of the challenges that you have. One is AI applied directly can overcome some of these challenges. So if you are, for example, struggling with not being able to process data accurately enough, then stronger AI tools can help you do a better processing. But also, what happens is if you are able to come up with explainable AI and you are able to provide to the user why certain things are happening, if they are indeed happening, then you could potentially enhance the experience. And once you enhance the experience, then this distortion such as cyber sicknesses or such other problems can be avoided. An easier way to relate to this is this concept of concierge or quality of experience in today's video conferencing. So whenever you have a video conferencing or you have an online lecture of this kind, there might be times when certain links might go bad. Now, if we can provide the user with the knowledge of what might be going wrong, he can, for example, switch off the video, or that video can be automatically switched off. The resolution can be adaptively changed. So changes can be made such that the quality of experience is monitored, if possible corrected, or at least informed to the user. Now, such things, when they are extended to the space of AR, VR, perform something very similar. So what explainable AI, so the next bullet is about what explainable AI primarily is. If you haven't gathered that already, all that it does for you is that it tells the user how and why the AI made the particular decision. And this is something that makes it easier for people to deploy AI solutions, because unless you do that, it's very, very, a lot of people are circumspect about using AI because they don't know what it's doing for you and how much of it it understands, and how much of it is just doing because it was probably trained correctly or incorrectly. So the next bullet is about mitigating cyber sickness, for example. Okay, so now coming to the next resolution, which is LIDAR. Like I said, for good quality experience, not only do you need visual cues, you also visual cues by way of content, you also need the depth information. So remote sensing and mapping, it can be made faster by use of LIDAR. So LIDAR is becoming commonplace. It is relatively costly, but with time, it is becoming smaller in size, cheaper, and more commonplace. A lot of phones today have some degree of LIDAR capability inbuilt, and this is what is taking the experience of AR, VR to the next level. So the next two bullets talk about some of the capabilities of LIDARs today. And these numbers, the higher they are, the better it is. And what these numbers essentially tell you is that you now have the capability to get a very high resolution, high accuracy map of the environment around you. And the moment you combine this with hyperspectral cameras or optical cameras for that matter, then you can get content which is extremely, extremely high quality, and it can do a lot of good in terms of visualization. And this is increasingly finding applications in geospatial kind of scenarios where people are using this for weather prediction, for understanding the quality of terrain, and also for defense applications. So high quality range information combined with dense at band and spatial resolution level data from, let us say, an optical camera or a hyperspectral camera. Combine all of this and you can potentially offer to the user a very high level of experience in terms of augmented reality. Can we move to the next slide, please? All right, more details vis-a-vis the LIDAR. This is a slide we can possibly skip. Can we please move to the next slide? These are more details. Interested people can look at it. Okay, so now the problem is that LIDAR is good for one thing, but it is it's not a one solution for all the ills or all the problems that exist. So you cannot work with LIDAR alone. And this is what brings us to computer vision, where you will have regular optical cameras, and using those optical cameras, you can have better object recognition. You can have better, so what is known as dense tagging. You can tag all the objects. You can tag the characteristics of each of those objects. You can tag the relationship that exists between these objects. And finally, as these objects interact with each other, you can update the relationships between these objects, and therefore have a very high level of information content about the scene. And once you combine this with realistic range information, you can potentially produce high quality content for AR and VR consumption. So these are just the names of some techniques, but by no means these are the only ones that you'll wish to use. These are just indicative, if anything. And using automated or semi-automated LIDAR for complex high definition 3D maps is becoming increasingly popular. GIS provider ESRI, it has used machine learning to replace 50,000 labor hours by automated detection of poles and power lines. So this is not about replacing people with machines, it's about easing the whole work. So this is one aspect of what these mechanisms can do. But these when they come into the fold of AR, VR, what they're doing for you is converting all of this data automatically into digital. Therefore, it is very easy to consume it in the form of AR, VR when required. Next slide, please. Okay. So then there is something known as neuromorphic imaging. Here you want to do imaging in a manner which is similar to the human retina. And this primarily looks at change detection more than the actual information that is present. So cameras today are not optimized to detect change. They are primarily optimized to collect the light amount of illumination falling on the sensor as accurately as possible, because the processing follows. So the idea was that the scene should be captured with as much fidelity as is possible. However, with more and more applications becoming AR and VR, and the need for real-time processing to start taking place, some of this information might be redundant, might be too heavy and avoidable. So this is what usually happens in the way the humans quickly adapt to the environment around them. They look for changes, they react to changes, they look at information carefully once a change has occurred. So they don't keep on collecting information about the environment at a very high rate, even if there is no change happening. So if you look at the fifth bullet, what it says is, this allows a neuromorphic camera to sample the environment with much higher temporal resolution, because it is not limited by the frame rate of a normal camera. So you're doing background suppression because it isn't changing. All that you're interested in is a change, because as long as a change does not happen, you really do not need to focus on it. And the moment there's a change that happens, you want to react to it. So spiking networks is another name given to them. So can we move to the next slide? So the neuromorphic cameras also allow for a very high dynamic range, which means that irrespective of the light conditions, you can get an idea of what's happening around you. Yeah, next slide, please. Okay, a little more on neuromorphic imaging. So because of all the advantages, because of all the properties that we just talked about, you will end up with not just a more human-like information, because it has to eventually be consumed by a human. You will also be able to reduce the power requirements, and also data compression becomes much easier. And because you are focusing on change, the ML algorithms that have to run on top of the data are lighter and therefore faster. So essentially what is happening is, by trying to look at the data in a way that the human eye and brain does, what you're able to do is you are also able to make in a machine able to make much faster reaction time. You use lesser amount of energy, because the way nature evolves is it does a balance of what is it that a particular amount of energy gives to you in return. So if an eye and brain is consuming too much energy just to give you an idea of the surroundings, it will be a capability that will be lost over time. But that is not what has been happening. Vision is becoming stronger and stronger as time passes. And the primary reason for that is, even though it's an important cue, it is extremely power efficient, the way humans see the world around them. So there is reduced power requirements. Data compression is automatic, because you're not trying to look at the same thing again and again and try to make sense of it. There's background suppression. You only looking for changes, and once the change happens, your responses start triggering. And because reactions are trigger driven, they are much quicker. So whatever advantages the human visual system has, and therefore has emerged as a winner in the story of evolution, is now being provided to machines, so that in the AR VR race, neuromorphic imaging can also turn out to be the fittest of the device for performing the tasks at hand. Next slide, please. And here, I think we have one more slide on neuromorphic imaging, which sort of shows us how we try to look at information by the human visual system. So the key innovation is that not only does it sense the present, it also has a memory of the past. And once you have a memory of the past and the present frame, what happens is it is easy to extrapolate and come up with the future trajectory predictions. And that is primarily what a human being does. So to avoid collision, he's looking at what information he already has and what could be the future location of the objects around him. Will it lead to a collision, for example? So conventional sensing looks at the current frame. In retinomorphic sensing, you look at the past and you look at it till the present, and you also have an idea of what might happen in the immediate future. So all of this together helps you interact with your environment better. It is power efficient and it is lighter to process. And therefore, if you incorporate such sensing and such acquisition in an AR, VR environment or setup, you stand to lower the latency and have a more realistic experience as opposed to that with current devices. Next slide, please. Okay, having looked at some things that matter for AR, VR becoming a reality by way of what it means to humans. So we've looked at, and please understand that because this is simply 45-50 minute lecture followed by a few discussion points, there's only so much that we can cover. This is by no means a comprehensive coverage of what AR, VR needs to be. Just a few interesting points related to one. When you combine the different aspects of image acquisition and about what happens when you sort of adapt your devices. So this is evolution of the machines in some sense. While humans evolved by, or animals evolved by way of survival of the fittest, here, based on our understanding of nature, we are trying to evolve the machines to a level where they become the right fit for AR, VR applications. Okay, next slide, please. Let's look at some applications now. So simulation training. Now, this is possibly one of the most well-known application of AR, VR. Today, when we think of AR, VR, one of the first thing that comes to mind is possibly training somebody without having the person to travel to a particular place, without that person having access to all of that equipment. You could overlay all of that information, and you could have a person sit remotely at his house and get a hands-on training, if you will, of the task at hand. So just to give you an idea of, let me paint a picture. So if you want to train a mechanic to handle engines, if you can put a headset, so he can see an engine and an engine seated in a car of the make that you wish it should be, and he could wear gloves and restraints, a bodysuit, which will provide it the kind of haptic feedback that you expect. So if a nut is tight, it will take a lot more effort to loosen it. So all of that experience can be given to the person by the way of the haptics feedback and the visual feedback and the audio feedback. All of that together can be given to the person. So while with the person having no access to the car, the tools, or the workshop, he or she is able to feel his or her way around working on an engine. So this is what potentially AR and VR can do. In VR, of course, it would be a training where you could see another mechanic or an avatar of a mechanic working on an engine, which is not as effective in training. But if you could also incorporate AR, simply by overlaying information to begin with, and then including even haptics feedback at a later stage, what you potentially are able to do is train a person at any location, and the trainer could also potentially be at any location. So the best trainer could be the person you learned fixing the engines from. Next slide, please. So what happens here is that by incorporating user interaction with the environment, now this is what VR is able to do. You are able to train a lot more people, and obviously it is cost effective. And the other advantage is you can train a lot more people by trainers who are sought after. The best trainers in the world are potentially available for you to get trained from. It can help people understand the workplace environment without actually going there, and therefore the issues related to safety and hurt to them or injury to them, all of those can be avoided. And to help those very workers master very, very expensive machines, so you do not give those machines directly to them, because they might end up spoiling them or causing them to develop a fault. So it is better to train them in a virtual environment, and when they are finally given access to the expensive machines, there is very little likelihood that they will use it incorrectly and therefore spoil it. And now similarly for doctors, they can do multiple scenarios without jeopardizing a single life. Flight simulators already do this, but it's quite a complex environment. You have to be seated, and those simulators are reasonably expensive. But as AR VR tools become smaller and more commonplace, cheaper, and more feature rich, there'll be a lot more training scenarios that will then be able to be handled. And therefore, you could have the best of doctors trained. One thing that we must understand is till such time as the experience using AR, VR becomes as real as the experience in the real world, people might have to train to work with the differences. So a doctor operating using a haptic glove might have to work slightly differently from a doctor who's actually using actual scalpels and scissors to perform the surgery. Next slide, please. Okay. Another area that comes to mind is defense and military, and here lots of changes have already happened. There is this example of something known as ARC4, which is augmented reality for, I think, command, coordination, communication, and something else. So there are 4 C's there. So what is happening here is that for tactical solution, situational awareness, you are able to augment the capabilities of the soldier by providing him with night vision, for providing him with information about things that he cannot directly see, which are not in the line of sight, which are behind walls. So essentially what is happening is that in defense and military, the more a soldier knows about the situation around him, the better he can perform. So tactical situational awareness is probably even more important than the weapon that the soldier carries. So a better informed soldier is probably more likely to win the battle than a better weaponed soldier, but not really aware of what's happening around him or her. So therefore, in the next era of defense and military, there will be a much larger role played by augmented reality than will be played by the weapons. Weapons, of course, will continue to improve, but they are already reasonably good, right? The weapons today can easily kill the enemy that you want to. But what you do not have today is the ability to have very, very high quality and reliable situational awareness. Can we move to the next slide, please? All right. So what are some of the things? So these are specifics that can happen. You can have better object recognition. So for example, if you have enemy in camouflage, you could quickly identify them before they identify you. If you have snipers, you're some distance away, hidden from view, you can identify them and move out of their line of sight. Vision can help you respond to your environment real time. If there's an incoming hostility, you could move away or plan not to move in a certain direction. If you know that there's a minefield in front of you, you could take a detour or do a mine sweep before you move further, and all of such things. And then NLP can help you understand the commands better. There can be no mistake in what is being said to you because it wasn't loud enough or it was spoken too quickly. So natural language processing can easily make sure that each soldier knows exactly what his or her order is. And predictive analytics based on what's happening around you and based on what you know and what you could be told about how the situation will change, and therefore how should you react in a proactive manner rather than react to the changes after they've happened. So AI is playing a role in each one of these, and therefore what we say is that AI has the power to bridge the gap between reality and simulation. Next slide, please. So this is just an example of what will happen, what is happening now, and this will only get better with time. Next slide, please. All right, this is another area where this might not seem as high tech, but this is much, much more commonplace. And this is something that can help you overcome irritating experiences where you talk to customer support and you end up being dissatisfied or irritated. So VR chatbots are something that happen much more often than soldiers traveling to battlefield. So virtual reality chatbots can potentially enhance the experience of a person when he wants information or when he wants certain things corrected. Either ways, chatbots have a huge role to play in our day-to-day life. As it is, almost all websites now have a chatbot. And if anything, this is something that will grow with time. So why is VR important in chatbots? So because once you have these chatbots have to understand what the human is saying, and they also have to understand what the human might expect in return, and what is it that the human can be given in response to the situation and his expectations. So VR chatbots, if they are programmed correctly, can deliver to the consumer an experience which is higher than what another human can give. A human can get tired, a human could be angry, a human could be upset. So a human chatting with you to fix your problem or to provide you a solution is at the end of the day a human. As opposed to this, when the same task is handled by a chatbot, the chatbot, being a machine, will not tire. It will have access to AI to understand the context, to understand the other human better, to understand what the person is trying to say, and it will obviously have access to a lot more information. LLM, large language models, and chat GPT, why has it become so popular and why is everybody talking about it so much? Because it gives you answers that it's difficult for a human concierge to give to you. So clearly, not every chatbot needs to be trained to the level of LLMs, but how can you leverage those LLMs and have VR chatbots which are specific to the application that is of interest? And how can this virtual chatbot become potentially a better employee for the organization offering you a solution? Next slide, please. So further, you could also so this is what the text could come to you, because it's a chatbot. So so you could expect text to be typed by it, but you could also have, on the other hand, avatars who could also speak to you, for example, or also make the right gestures while they speak. So all of that is possible, but then you move beyond chatbots and you have human-like support. But the idea is the same. So primarily, the things are, how do you increase the engagement level? A human being, when he sits at one end of a telephone line or at one end of a chat discussion, he is, well, at least he should be trying to make sense of what the state of mind of the other person is, where is the other person coming from, and what are the right set of responses that I should give, given his expectation and given what can be offered to the person. But AI can do it better for restricted scenarios. If the scenario is restricted, machines have repeatedly and decisively outperformed humans in such tasks. So VR chatbots are going to become more and more feature-rich. They're going to become more and more engaging, and they are going to become more satisfying to the consumer when they interact with them, as opposed to interacting with humans at the other end. Next slide, please. And then there is this concept of digital twin, where you move from a reactive approach to a preventive one. You map all the information that you need for a particular scenario, digitize it, put it through its paces, and you already know what are the problems that you might encounter, either fatigue in a machine, or the possibility of it going faulty. All of that will be available to you even before that fault actually happens. So by digital twin, what you can do is you can bring a lot more information into the digital domain, and then you can put this digital twin through its paces, and that in turn can tell you what might happen to the real physical device when it is put to use. And therefore, what will happen is that tomorrow, because of AR along with AI, we will be able to take a proactive or preventive approach to work rather than a reactive approach. We won't have to wait for a machine to go down before we send it out for repair. We will ensure that timely repairs happen so that it does not go faulty at all. Next slide, please. Okay, so here we talk of how LIDARs might play a role in digital twin, where LIDARs can collect data and AI can then perform some kind of processing on it. And so here LIDARs, because they give you an idea of depth, they can be used to create point clouds. So point clouds are 3D representations of objects. When you see an image, that's a 2D representation of the scene around you. Now, if you replace this by point clouds, which is a collection of the distance a particular point is from you or a particular reference point, then you get 3D models for objects of interest. So LIDAR can quickly build 3D models of the objects of interest and digitize them, and then you can do whatever experimentation you want to on the digital twin, and then use the learnings to use the physical device more correctly. Next slide, please. All right. Okay, here we're talking of two types of radars, airborne and terrestrial. We'll skip this. We've spoken a lot about LIDAR. I think next slide, please. Okay, then come medical surgeries. This is probably the last application that we'll look at, and then we leave some time for question answers. So in medical surgeries, again, this is something that will change, and the way we look at it is that today AR, VR, VR can be used for training and AR can be used for performing surgeries in a better manner. So while the doctor looks at a particular body part, you could overlay more information on top of it so that you can perform the surgery better, you can make lesser mistakes, and there can be a higher degree of accuracy. Now, what also happens is, this is different from robo-assisted machine surgeries. That in robo-assisted surgeries, what happens is that the robo uses machine precision to perform the tasks very, very accurately. In AR-assisted surgery, what happens is you get overlaid information so that while you perform the particular operation or the particular surgery or whatever it is that you're doing, you have all the necessary information that you need as you go about doing it. Something like the helmet of the fighter pilots, where on the on the glass in front of the helmet, you get all the information that you need so that you have high situational awareness. Here again, the vital conditions of the person and any other information that needs to be had can be overlaid, and therefore you will be able to perform the task a little better. Next slide, please. And this is simply an example of how it would assist a doctor wearing a headset, performing the surgery. Next slide. Okay, right. So in conclusion, what we are saying is that LIDAR was about depth perception, and AI/ML is about being able to perform analysis. So given depth information and given the capability to analyze, what happens is that AR and VR applications and solutions potentially become stronger. So we have seen how that happens by understanding something about how LIDARs work. We have tried to understand how AI/ML has issues which can be taken care of if we, for example, take some cues from the way human visual system works, and how explainable AI can have a role to play, and how AR, VR is no longer a question of if, but it is a question of when. So I'll stop here now and take questions if there are any.
Thanks a lot, Professor Brajesh, for this nice presentation and explaining all the intricacies of AR, VR combined with AI. So right now, I'd like to invite Vishnu. Hi, Vishnu. Good afternoon or evening.
Yeah. Thanks, Thomas, and thanks, Vijay, for that excellent talk. I remember our previous two talks. I think they were quite amazing. But now you're very simple manner. I think Vijay has laid out the land. The lay of the land is quite clear for AI and AR VR technologies. Thank you so much. By the way, we invited Brajesh for the AI for Good Summit. There is a workshop, and unfortunately he couldn't make it. Thank you for at least taking the time today to come to us. There is a question. Semantic communications can be used by neuromorphic image sensor to reduce latency. I wonder, whether it is the other way around or not. I want to ask Brajesh. The semantic, in fact, if you look at your layout, what you had laid out in the slides, the data collection, you talked about data collection in the sense of neuromorphic sensors. Then you looked at semantic communications in the sense of pre-processing and communications, and then you looked at actuators and the impact towards it, right? So how can semantic communications used by neuromorphic image sensor to reduce latency? That's the question. I will leave it to you, Vijay.
Thank you, Vishnu. Thank you for also, setting making it clear that what this is about. So essentially neuromorphic, because we are already capturing in some sense semantic information, because you're looking at change, you are doing background suppression, so you already converting data, and I'll call it data and not information, into information. So you're only capturing, if you will, information. So a change is information in context of survival. So in a predator situation, if you can detect a change, a predator moving, on the side, you'll probably survive. So because it is only capturing information, so it is the kind of fuel that semantic communication needs. The semantic communication will only work if there is a mechanism to generate enough amount of semantic data. Typically, in today's world, what happens is we have a lot of syntactic data. To use semantic communication, we will first have to convert that into semantics and then send it over the communication channel that we've set up. Now, with devices like neuromorphic imaging tools, what will happen is that some of the information they generate will be closer to semantic than to syntactic. And therefore, they can more easily be transmitted over semantic kind of scenario. So yes, such devices, more of such devices, the better it is for people in this area.
Thank you so much. I actually that leads us very nicely to the next topic, that is of we had this question of AR native. I mean, these days everybody talks about AI native, cloud native, and so on. But I want to ask you, what is your take on what is AR native? What I mean is that will there be applications in future which primarily are built for AR, VR environments, so to speak, rather than the physical environments? That's the first thing. Second thing is, as a developer, I would develop an application. Would I think of first platform as AR, VR as a deployment target instead of physical environment or a mobile or whatever? What is your take upon this, especially considering your just now you answered about semantic communications, right? There is a link between this. As a developer, if I build solutions AR native, that's a different ball game altogether.
Okay, so that's a very, very important question. Now, there are two aspects to this. There is a push and then there is a pull. One negative, one positive. So what is happening is AR, VR is primarily for human consumption. Machines do not necessarily need AR, VR because they do not experience, they perform. Now, what is happening is that the machines are slowly increasing in number. So with every passing year, the ratio of machines to humans as the consumers of compute tools, comm tools, the number of machines is going up, and it will keep on growing. So what is happening is, so the percentage of people looking for AR, VR is reducing. But on the other hand, the expectation of this minority, if you will, even 20 years from now, their expectation is rising, which means that they are no longer satisfied with what the physical world has to offer to them. So AR, VR native applications is something that will become a reality, not today. It will have to start with VR, because VR is slightly easier than AR, because in VR, everything is in the virtual world. So it is a little more controlled. In AR, what happens is you need to combine the real world with new information that you want to input into the scene. And that is slightly tougher than moving entirely to the virtual world. So the way I see this happening is there'll be a lot more virtual reality. Then there will be a lot more augmented reality. Virtual reality will give way to augmented reality, and augmented reality will continue to rise because this minority of users will have exponentially rising expectations, because humans are extremely difficult to satisfy. They get used to something very quickly, and then that no longer satisfies them. And that is why you would see a lot more people spending time on social networks than engaging with people in the real world. It is very difficult to get appreciation in the real world. But you click a photograph and some relatively unoccupied people will give you a few likes, and all of a sudden you get a high of having probably clicked a masterpiece. So that is the kind of satisfaction you expect. But now if you click a photograph and show it to one person and you have a critical discussion over it, you cannot expect to get the same level of dopamine or whatever it's called, the feel good. It won't happen. So what is happening is we are spoiling ourselves. We are getting used to more and more of non-real experiences, and therefore augmented reality is something that will become more and more commonplace. It will become more and more in demand. I'm not advocating that it should. I'm simply stating a fact based on what I see happening around me.
Cool. Yeah, maybe I will squeeze in one last question. So the role of standards. You mentioned ontologies. You mentioned standard structures. But in this talk, you haven't gone to the level of APIs or architectures or such things, right? So maybe let me ask you beforehand, what role of standards do you see here? Especially, you just now talked about machines as consumers. Their interoperability is definitely a problem. So definitely there is a role of standards. But what exactly is it? Especially when you look at machines as consumers and agents, software agents which are native to this AR. So what kind of standards are you looking at to play in this space?
Okay, so thank you. That's a very, very good question. First, let me tell you why I did not talk about standards in this talk. So the reason I left standards out is that this field is evolving. Okay, and standards is a constraint. Now, to some people, knowing that standards is a given, this is a reality of this space, will make them work aligned to a standard. For some other people, it kills creativity. Now, creative people are ones who come up with usually more innovative and more exciting solutions. So this talk was more about enthusing people about the challenges of AR, VR, and how this is something that will come and become part of our lives, whether we like it or not. Now, coming back to the role of standards, these things will not happen without standards, because the humans or living things evolve a certain way. Machines do not have that constraint. So a company XYZ will make a robo of one kind, they will make a robo of another kind, and both can survive because there are no environmental pressures on them because there's somebody who's nurturing them. So what is going to happen is you will get many more species. Now, unless there is standardization at some level, you will end up with a situation where you have capable devices, but you can't use them. You can't make them part of an ecosystem. So there will be need for standardization, not just in communication, but also in the way these interact with the environment. So you'll have to standardize the way they collect information, or at least in the way they represent them. Then speaking the same language, semantics, even though it sounds all exciting, it is, while you work with digital data, everybody is talking 0 1s. So it is in some sense standard. But the moment you move to semantics, there is no standardization that is natural. So you will have to build in standardization in the way you represent semantic information. So earlier there was the need for standardization at the communication level. Now it will move a couple of steps backward. Communication will need standardization, but so will the need to represent, so will the need to acquire, and so will the need to actuate. So control, compute, and communication all will now be forced to work according to a standard, or if they don't comply, then they'll die a natural death, because you will not be able to influence enough number of people to survive on your own.
Cool. Yeah. Thanks a lot. Thanks a lot. Yeah, I think your group, especially from IIT Delhi, Vijay's group's actually at the sweet spot of DSP, signal processing, AI, AR, VR, and communications. So I think we would look forward to the exciting research from your group. We are 6 minutes way off. Thank you so much for taking the extra time and answering the questions. And once again, we look forward to your exciting research in future. Thanks, Vijay. Back to you, Thomas.
Thank you so much, Vishnu, for the Q&A, for the good discussion. And I would like to take this opportunity also to thank Professor Brajesh for making time describing this interesting topic to us. And really, we thank you for all the collaboration that has been happening with us, and we look forward to further new opportunities, further collaboration in future. I would also like to thank everyone who joined the session today. Thank you for making time. And I would also like to make an announcement that the ITU and Machine 5G challenges are open. We have problem statements that are ongoing. We are going to launch more problem statements in the coming weeks, so stay tuned. For more of our programs and webinars, you can see the AI for Good program page, where you can see our upcoming webinars. So from me and my colleagues, I would like to wish you a very good day, and thank you everyone for joining the session. Have a lovely day. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.